Mountain environments are extremely vulnerable to climate changes, and often landslides, floods and avalanches can put at survival risk small towns and villages. Any realistic strategy to counter these risks is necessarily based on constant monitoring and on a thorough maintenance activity. Maintenance operations are currently executed by specialized personnel, able to reach the operation areas through mountaineering techniques and to execute complex operations while hanging from a rope. The scarcity of personnel with these skills and the inherent danger of the environment suggest the application of a robotic solution. The solution should satisfy vital requirements that are out of reach for conventional solutions, namely, carry a heavy payload, be able to move quickly along the wall, to overcome obstacles on the way where the robot could be trapped, and finally, be autonomous in performing maintenance operation. Taking inspiration from human climbers, we propose a robotic platform able to move and reach targets along steep mountain slopes. The robot will move by using the combined action of two ropes attached to the top and a prismatic leg that can be extended and retracted very quickly. The leg is used to make the robot jump by pushing it quickly away from the slope, while the ropes are unwound to control the motion during the flight phase. Finally, a landing mechanism allows the robot to land. Contrary to flying vehicles, the ropes allow to carry heavy payloads and be stationary on the wall without energy consumption by engaging brakes. The combination of mixed vertical lateral motions allows the robot to move quickly and efficiently. 3D movements allow to swing over the wall surface, overcoming obstacles. A landing mechanism allows the robot to dissipate the excess of kinetic energy and stay firm on the wall. There is a number of scientific challenges that set the stage for ambitious research activities in both control and planning. First, the dynamics is nonlinear, under-actuated and hybrid. Second, one of the actuators, the retractable leg, operates in an impulsive way, while the ropes can only develop forces in the pulling direction. Third, the robot should be able to deal with irregular and varying terrain, avoiding natural obstacles. Fourth, a kinematic loop appears in the two anchor setting. These challenges makes the platform a good candidate for optimal control techniques. We present a numerical procedure to evaluate the static stability of the robot for a set of locations, once landed on the wall. The robot plus the landing mechanism is modeled as a single rigid body. We evaluate maximum operation forces that can be tolerated while satisfying static condition, unilateral, friction and actuation constraints. The feasible wrench polytope is a compact representation of the mentioned constraints projected at the center of mass. The feasibility margin gamma in the direction v is the distance between the gravitational wrench and the polytope boundary. It is a synthetic metric to estimate the amount of external forces and moments available for operations. As an example, we compute the heat map of the feasibility margin for a drilling operation for two different wall inclinations. To plan the jump trajectory, we transcribe an optimal control problem into an NLP where the decision variables are the trajectories of the rope forces, the leg impulse, and the duration of the horizon. The states are the chosen coordinates and their derivatives, and are computed with the reduced order dynamics along the whole horizon. In the cost function we have three terms. One minimizes the variation of the rope forces, another their energy consumption, while the third the kinetic energy at the landing. There are several physical constraints in the system, bounds on the rope forces. On the leg impulse we have friction constraint that relates the tangential to the normal component. The last two constraints are included to ensure that the motion is in front of the wall and avoid obstacles. Finally, we embed the solution of the optimal control problem in the full model for simulation. The trajectories of the rope forces are driving the prismatic joints. We model the attachment of the rope with the anchor and the base through passive joints. The leg impulse is mapped into the leg torques through the dynamic equation. Because we apply the impulse at the contact and not at the center of mass, this can create centroidal moments that could generate pivoting motions with respect to the rope axis. To mitigate this issue, we orient the leg along the impulse direction. We implemented an MPC controller that acts both on rope and propeller forces. To evaluate the effectiveness of the MPC in tracking and rejecting disturbances during the flight phase, we applied an impulsive and a constant disturbance to the robot base. Here we see the reorientation phase where the leg is aligned with the optimized impulse direction. Alternatively, a pair of differentially driven propellers could be used to reorient the leg.
Next, we present simulation results that show how the control inputs obtained running the optimization are able to bring the robot to a number of desired targets evenly distributed on an ellipse around the same liftoff location on the wall. In this experiment we test capability of the optimal planner to deal with a non-flat wall surface. We model an obstacle as a hemi-ellipsoid. If the obstacle is too high, multiple intermediate jumps could be undertaken to overcome it. The planning approach is able to deal with any wall inclination up to vertical. Here we show examples of upward and downward jumps on slanted walls of different inclinations. In another experiment we assess effectiveness of the kinematic strategy to correct the misalignment of the landing legs with the wall created by the action of a disturbance, and the capability of the landing strategy to dissipate the excess of kinetic energy at the touchdown, resulting in no rebound. Once landed, if the wall is clear from obstacles, the position can be efficiently adjusted by actuating the landing wheels. In a final simulation, we demonstrate the versatility of the approach in providing valid results for different placements of the anchor points.